South-pointing chariot. The south-pointing chariot or carriage was an ancient Chinese two-wheeled vehicle that carried a movable pointer to indicate the south, no matter how the chariot turned. Usually, the pointer took the form of a doll or figure with an outstretched arm. The chariot was supposedly used as a compass for navigation and may also have had other purposes. The ancient Chinese invented a mobile-like armored cart in the 5th century BC called the Dongwu Che Chinese, Dongwu Che. It was used for the purpose of protecting warriors on the battlefield. The Chinese war wagon was designed as a kind of mobile protective cart with a shed-like roof. It would serve to be rolled up to city fortifications to provide protection for sappers digging underneath to weaken a wall's foundation. The early Chinese war wagon became the basis of technologies for the making of ancient Chinese south-pointing chariots. There are legends of earlier south-pointing chariots, but the first reliably documented one was created by the Chinese mechanical engineer Ma Jun c. 200–265 of Cao Wei during the Three Kingdoms. No ancient chariots still exist, but many extant ancient Chinese texts mention them, saying they were used intermittently until about 1300. Some include information about their inner components and workings. There were probably several types of south-pointing chariot which worked differently. In most or all of them, the rotating road wheels mechanically operated a geared mechanism to keep the pointer aimed correctly. The mechanism had no magnets and did not automatically detect which direction was south. The pointer was aimed southward by hand at the start of a journey. Subsequently, whenever the chariot turned, the mechanism rotated the pointer relative to the body of the chariot to counteract the turn and keep the pointer aiming in a constant direction to the south. Thus, the mechanism did a kind of directional dead reckoning, which is inherently prone to cumulative errors and uncertainties. Some chariots' mechanisms may have had differential gears, technology unseen since the ancient Greek Antikythera mechanism. Historical texts. Earliest sources. The south-pointing chariot, a mechanical geared, wheeled vehicle used to discern the southern cardinal direction without magnetics, was given a brief description by Ma's contemporary Fuxuan. The contemporary 3rd century source of the Weilu, written by the East Han Dynasty politician Yuan Huan, also described the south-pointing chariot of belonging to the Chinese mechanical engineer and politician Ma Jun. The Jin Dynasty 266–420 era text of the Shuzhengjai records of military expeditions, written by Guo Yuansheng, recorded that south-pointing chariots were often stored in the northern gatehouse of the government workshops, Shangfang, of the capital city. However, the later written Song Shu Book of Song 6th century recorded the south-pointing chariot's design and use in further detail, as well as creating the background legend of the device's supposed use long before Ma's time in the Western Zhou dynasty 1050–771 BC. The book also provided a description of the south-pointing chariot's reinvention and use in times after Ma Jun and the Three Kingdoms. The 6th century text, translated by the British scientist and historian Joseph Needham, reads as follows: the south-pointing chariot is referred to as the south-pointing carriage. The south-pointing carriage was first constructed by the Duke of Zhou beginning of the 1st millennium BC as a means of conducting homewards certain envoys who had arrived from a great distance beyond the frontiers. The country to be traversed was a boundless plain, in which people lost their bearings as to east and west, so the Duke caused this vehicle to be made in order that the ambassadors should be able to distinguish north and south. The Guiguzi book says that the people of the state of Zheng, when collecting jade, always carried with them a south pointer, and by means of this were never in doubt as to their position. During the Qin and former Han dynasties, however, nothing more was heard of the vehicle. In the later Han period, Zhang Heng reinvented it, but owing to the confusion and turmoil at the close of the dynasty, it was not preserved. In the state of Wei in the San Guo period, Gaotong Long and Qin Lang were both famous scholars. They disputed about the south-pointing carriage before the court, saying that there was no such thing and that the story was nonsense. But during the Qing long reign period 233–237, the Emperor Ming Dai commissioned the scholar Ma Jun to construct one, and he duly succeeded. This again was lost during the troubles attending the establishment of the Jin dynasty. Later on, Shi Hu, emperor of the Jia later Zhao dynasty, had one made by Zai Fei, and again Ling Husheng made one for Yao Xing, emperor of the later Qin dynasty. The latter was obtained by Emperor and Dai of the Jin in the 13th year of the Roman XI reign period 417, and it finally came into the hands of Emperor Wu Dai of the Liu Song dynasty when he took over the administration of Chang'an. Its appearance and construction was like that of a drum carriage automator. A wooden figure of a man was placed at the top, with its arm raised and pointing to the south, and the mechanism was arranged in such a way that, although the carriage turned round and round, the pointer arm still indicated the south. In state processions, the south-pointing carriage led the way, accompanied by the imperial guard. These vehicles, constructed as they had been by barbarian king workmen, did not function particularly well. Though called south-pointing carriages, they very often did not point true, and had to negotiate curves step by step, with the help of someone inside to adjust the machinery. The ingenious man from Fanyang, Sai Zhu Changzhai, frequently said therefore that a new and properly automatic south-pointing carriage ought to be constructed. So towards the close of the Shang Ming reign period 477–479, the Emperor Shun Dai, during the premiership of the Prince of Kai, commissioned Zai Zhu Changzhai to make one, and when it was completed it was tested by Wang Sengkian, military governor of Tanyang, and Liu Hsiu, president of the board of censors. The workmanship was excellent, and although the carriage was twisted and turned in 100 directions, the hand never failed to point to the south. Under the Jin, moreover, there had also been a south-pointing ship. The last sentence of the passage is of great interest for navigation at sea, since the magnetic compass used for seafaring navigation was not used until the time of Shen Kuo 1031–1095. Although the Songshu text describes earlier precedents of the south-pointing chariot before the time of Ma Jun, this is not entirely credible, as there are no pre-Han or Han Dynasty era texts that describe the device. In fact, the first known source to describe stories of its legendary use during the Zhou period was the Gu Jinzhu Book of Kui Bao C. 300, written soon after the Three Kingdoms era. Kui Bao also wrote that the intricate details of construction for the device were once written in the Shangfang Gushi traditions of the imperial workshops, but the book was lost by his time. Japan. The invention of the south-pointing chariot also made its way to Japan by the 7th century. The Nihon Shoki, the Chronicles of Japan of 720, described the earlier Chinese Buddhist monks Zhai Yu and Zhai Yu constructing several south-pointing chariots for Emperor Tenji of Japan in 658. This was followed up by several more chariot devices built in 666 as well. Songshi. Chariots with differential gears. Background and explanation. There is a widely believed hypothesis that most, if not all, south-pointing chariots worked by means of differential gears. A differential is an assembly of gears nowadays used in almost all automobiles except some electric and hybrid electric ones, which has 3 shafts linking it to the external world. They are conveniently labeled A, B, and C. The gears cause the rotation speed of shaft to be proportional to the sum of the rotation speeds of shafts B and C. There are no other limitations on the rotation speeds of the shafts. In an automobile, shaft A is connected to the engine through the transmission, and shafts B and C are connected to 2 road wheels, one on each side of the vehicle. When the vehicle turns, the wheel going around the outside of the turning curve has to roll further and rotate faster than the wheel on the inside. The differential permits this to happen while both wheels are being driven by the engine. If the sum of the speeds of the wheels is constant, the speed of the engine does not change. In a south-pointing chariot, according to the hypothesis, shaft B was connected to one road wheel, and shaft C was connected through a direction reversing gear to the other road wheel. This made shaft rotate at a speed that was proportional to the difference between the rotation speeds of the two wheels. The pointing dial was connected possibly through intermediate gears to shaft A. When the chariot moved in a straight line, the two wheels turned at equal speeds, and the dial did not rotate. When the chariot turned, the wheels rotated at different speeds for the same reason as in an automobile, so the differential caused the dial to rotate, compensating for the turning of the chariot. The hypothesis that there were south-pointing chariots with differential gears originated in the 20th century. People who were familiar with modern, e.g., automotive uses of differentials interpreted some of the ancient Chinese descriptions in ways that agreed with their own ideas. Essentially, they reinvented the south-pointing chariot, as it had previously been reinvented several times in antiquity. Working chariots that use differentials have been constructed in recent decades. Whether any such chariots existed previously is not known with certainty. Although the Antikythera mechanism is believed to have used differential gears, the first true differential gear definitely known to have been used was by Joseph Williamson in 1720. He used a differential for correcting the equation of time for a clock that displayed both mean and solar time. Geometrical properties. If the south-pointing chariot were built perfectly accurately, using a differential gear, and if it traveled on an earth that was perfectly smooth, it would have interesting properties. It would be a mechanical compass that transports a direction given by the pointer along the path it travels. Mathematically, the device performs parallel transport along the path it travels. The chariot can be used to detect straight lines or geodesics. A path on a surface the chariot travels along is a geodesic if and only if the pointer does not rotate with respect to the base of the chariot. Because of the curvature of the Earth's surface due to it being curved around as a globe, the chariot would generally not continue to point due south as it moves. For example, if the chariot moves along a geodesic, as approximated by any great circle, the pointer should instead stay at a fixed angle to the path. Also, if two chariots travel by different routes between the same starting and finishing points, their pointers, which were aimed in the same direction at the start, usually do not point in the same direction at the finish. Likewise, if a chariot goes around a closed loop, starting and finishing at the same point on the Earth's surface, its pointer generally does not aim in the same direction at the finish as it did at the start. The difference is the holonomy of the path and is proportional to the enclosed area. If the journeys are short compared with the radius of the Earth, these discrepancies are small and may have no practical importance. Nevertheless, they show that this type of chariot, based on differential gears, would be an imperfect compass, even if constructed exactly and used in ideal conditions. Lack of precision and implications. Real machines are never built perfectly accurately. Simple geometry shows that if the chariot's mechanism is based on a differential gear and if, for example, the width of the track of the chariot, the separation between its wheels is 3 meters, and if the wheels are intended to be identical but actually differ in diameter by 1 part in 1,000, then if the chariot travels 1 kilometer in a straight line, if it initially points exactly to the south, at the end of the 1 kilometer trip it will point almost to the south-southeast or south-southwest, depending on which wheel is the larger. If the chariot travels 9 kilometers, the figure will end up pointing almost due north. Obviously, this would make it useless as a south-pointing compass. To be a useful navigational tool, the figure would have to rotate no more than a couple of degrees over a journey of 100 kilometers. But this would require the chariot's wheels to be equal in diameter to within 1 part in a million. Even if the process of manufacturing the wheels were capable of this precision, which would not be possible with ancient Chinese methods, it is doubtful that the equality of the wheels could be maintained for long as they are subjected to the wear and tear of traveling across open country. Irregularity of the ground would add further errors to the device's functioning. Considerable skepticism is therefore warranted as to whether this type of south-pointing chariot, using a differential gear for the whole time, was used in practice to navigate over long distances. Conceivably, the south-pointing dial was fixed to the body of the chariot while it was traveling in straight lines, and coupled to the differential only when the chariot was turning. The charioteer could have operated a control to do this just before and after making each turn, or maybe shouted commands to someone inside the chariot who connected and disconnected the dial and the differential. This could have been done without stopping the chariot. If turns were brief and rare, this would have greatly reduced the pointing errors, since they would have accumulated only during the short periods when the dial and differential were connected. However, it raises the problem of how the chariot could have been kept traveling in straight lines with sufficient accuracy without using the pointing dial. If the real purposes of the chariot and the accounts of it were amusement and impressing visiting foreigners, rather than actual long-distance navigation, then its inaccuracy might not have been important. Considering that a large mechanical wagon or chariot would be obligated to travel on roads, the destination in question would typically not be in an unknown direction. The fact that the sources cited above mention that the chariot was placed at the front of processions, its high level of mechanical complexity and fragility, and that it was reinvented several times contribute to the conclusion that it was not used for navigation, as a truly practical and useful navigational tool would not be forgotten or left unused. Chariots without differential gears. Although the hypothesis that the south-pointing chariot used differential gears has gained wide acceptance, it should be recognized that functional south-pointing chariots without differential gears are possible. The ancient descriptions are often unclear, but they suggest that the Chinese implemented several different designs, at least some of which did not include differentials. Mechanical designs. Some of the ancient descriptions suggest that some south-pointing chariots could move in only three ways straight ahead, or turning left or right with a fixed radius of curvature. A third wheel might have been used to fix the turning radius. If the chariot was turning, the pointing dial was connected by gears to one or other of the two main road wheels, e.g. whichever was on the outside of the curve around which the chariot was moving, so the dial rotated at a fixed speed relative to the rate of the chariot's movement to compensate for the predetermined rate of turn. The dial turned in opposite directions depending on which road wheel was connected to it, so its rotation compensated for the chariot turning left or right. This design would have been simpler than using a differential gear. The chariots of Yansu and Wuduran appear to have used this type of mechanism. See descriptions quoted from the Songshi above. Apart from the presence of components in Wuduran's vehicle to make it function as an odometer, there were only minor differences between them. In each chariot, the two main road wheels were attached to vertical gear wheels. A large horizontal gear wheel was linked possibly via intermediate gearing to the pointing dial, and was positioned so a diameter almost spanned the space between the uppermost points of the vertical gear wheels. When the chariot was moving straight ahead, there was no connection between these gears, but when the chariot turned, a small gear wheel was lowered into contact with the horizontal gear and one of the vertical gears, thus linking the dial to one of the road wheels. Two small gear wheels were available, one to connect the horizontal gear to each of the vertical ones. Of course, they were not used simultaneously. The small gear wheels were raised and lowered by an arrangement of weights, pulleys, and cords which were attached to the pole to which the horses that pulled the chariot were harnessed. When the horses moved to one side or the other in order to turn the chariot, the pole moved and the cords lowered the appropriate small gear wheel into its working position. When the horses returned to walking straight ahead, the small gear wheel was raised out of contact with the main horizontal and vertical gears. Thus, the system functioned automatically. The mirror symmetry of the vertical gears being linked by the small gears to the horizontal gear at diametrically opposite points caused the horizontal gear to rotate in opposite directions depending on which road wheel was linked. The description does not mention a third road wheel to fix the turning radius, but it is possible that such a wheel was present. No gears would have been attached to it, so perhaps the author of the description did not mention it because he did not realize that it was an important part of the mechanism. Putting such a wheel on the chariot and making it function properly would not have been difficult. It might have been attached to the pole to which the horses were harnessed. Stops would have been provided to limit the motions of the pole to left and right. If a third road wheel was included, this type of south-pointing chariot could have worked quite accurately as a compass when used for short journeys under good conditions, but if used for long journeys it would have been subject to cumulative errors, like chariots using the differential mechanism. If in fact there was no third road wheel, the chariot might have functioned as a compass if turns were always made so that one of the two wheels was stationary and only the other rotated, with the pointing dial connected to it by gears. The charioteer could have kept the stationary wheel from turning by controlling the horses appropriately. A brake would have helped, but there is no mention of one in the description. The radius of the curve around which the rotating wheel moved would have equaled the track width of the chariot, and the gears turning the dial would have been chosen accordingly. This design would have worked as a compass for short journeys, but would have suffered from cumulative errors if used for long ones. Also, the chariot would have been slow and awkward to turn. This might not have mattered if turns were rarely executed. The Songshi description of the gears in Yan Su's chariot and the numbers of teeth on them suggests that it worked this way, without a third road wheel. The gear ratios would have been correct if the pointing dial was attached directly to the large horizontal gear wheel and the track width of the chariot equaled the diameter of the road wheels. Wu Duran's chariot also appears to have been designed to work this way. The width of the chariot, and therefore presumably the track width, was greater than the diameter of the wheels. The gear ratios were appropriate for these dimensions. The charioteer would have had to use great skill to ensure that the radius of each turn of the chariot was correct to make one of the wheels exactly stop rotating. Unless he did this correctly, the pointing dial would not have kept aiming to the south. He would have been able to adjust the direction in which it aimed by making turns that were more or less sharp. This would sometimes have given him opportunities to use the chariot dishonestly. If it was being demonstrated to spectators, for example, and was being driven around in front of them, making many turns, the charioteer, who would have known which way was south, would have been able to make the chariot appear to work extremely accurately as a compass for long periods. The spectators could have been shown the machinery and would have seen that the charioteer could not manipulate the dial. They would presumably have been impressed by the apparent accuracy of the mechanism. It is possible that this type of chariot was sometimes constructed with the prime purpose of fraudulently impressing spectators. Possibly, people who built these chariots deceived their own employers with them, which could have gained them fame and fortune provided nobody tried using the chariots for real navigation. Other mechanical designs for the south-pointing chariot are also possible, including ones that employ a device that is used today, the gyrocompass. However, there is no indication that the ancient Chinese knew of these. Non-mechanical possibilities. Some south-pointing chariots may not have been purely mechanical devices. Someone riding inside the chariot may have used some non-mechanical method of determining the compass directions and turned the dial on top of the chariot accordingly. There are several methods that could have been used, for example, by using a magnetic compass. The Chinese were using this for navigation by the 11th century, when south-pointing chariots were still being made and used. By using astronomical observations of the sun and slash or stars, e.g. the pole star. Chinese astronomical knowledge was extensive. By using local knowledge. The person in the chariot may have known the area or had a map or description of it. By observing the polarization of light from the sky. Vikings used birefringent crystals of Iceland spar to navigate across the Atlantic Ocean by this method at about the same time. Iceland spar is found in China, as well as in Iceland and some other places. Insects such as bees can respond to sky polarization and use it to find their way home. Whether the Chinese used it is hypothetical, but it is certainly possible. By observing light that had been refracted by the Earth's atmosphere. This is one of the techniques that were used by Polynesian navigators to steer ships among Pacific islands. When the surface of the earth, ocean, or ground is colder than the air above it, a dense layer of air is formed near the surface, which refracts light downward. The result is that light can go around the curvature of the earth, allowing things to be seen at much greater distances than simple geometry would predict. The images are very distorted, but they can be recognized by skilled navigators. Certain other Polynesian techniques can also be used on land and may have been employed by the Chinese. Unlike mechanisms that rely on the rotation of road wheels, most of these methods can be used at sea. This may account for the mentioned see earliest sources above that a marine version of the south-pointing chariot existed. These methods can work accurately over long distances, unlike the mechanical designs for the chariot. Necessity of non-mechanical orientation. Some non-mechanical method of finding the south must have been used when a mechanical south-pointing chariot was initialized, aiming its pointer to the south at the start of a journey. Any of the methods mentioned above in non-mechanical possibilities could have been used. If any south-pointing chariot was really used for long-distance navigation, it must have relied after initialization on a non-mechanical direction-finding method. It might have been operated non-mechanically by someone riding in it, as outlined above. Alternatively, if it had a mechanical mechanism, it must have been frequently reinitialized non-mechanically to eliminate accumulated errors and uncertainties. The only chariots that might not have needed non-mechanical methods of finding the south would have been those that were never used for long-distance navigation. If some chariots were used only for amusement or fraud, they could have worked purely mechanically. Even initialization could have been avoided by simply declaring some arbitrary direction to be south. Where they can be seen, while none of the historic south-pointing chariots remain, full-sized replicas can be found. The History Museum in Beijing, China, holds a replica based on the mechanism of Yansu 1027. The National Palace Museum in Taipei, Taiwan, holds a replica based on the Lanchester mechanism of 1932. Referred to as the Southern Pointing Man, two replicas can also be seen and physically experimented with at the Ontario Science Centre in Toronto, Canada.